atom was, the electrons outside the nucleus are attracted to the protons in the nucleus. So we know there's an attraction. So what keeps it from collapsing? We know we have charged particles moving in a curved path lose energy. So what keeps the atom from losing energy? And also what keeps the electrons and protons from attracting each other, because we know opposites attract. So J.J. Thomson, which we know he was responsible for discovering the electron, he said electrons behave as particles. So we know what a particle looks like. It's just like a little circle of like little circles. That's all we know about how electrons behave. However, his son, George, who won a Nobel Prize, just like J.J. did, said no, electrons behave more like a wave, and we know waves are forms of energy. So we know electrons are just our energy, and within the energy, the electron moves in a wave-like fashion. So when we think of a wave, we're thinking of, like, if here's my, not a very good origin line, but here's my origin, but if I'm drawing it, this is a wave, okay? So waves have certain characteristics, and we'll get into that. So I'm going to actually have you watch a video on Flame Test Lab, but really where this is coming from is the fact that electrons, chemicals, when you heat them up, they emit color, and we want to know where that color comes from. There was a guy who his name is Louis de Broglie, and he said electrons propagate through space as an energy wave. To understand the atom, one must understand the behavior of the electromagnetic waves. So if we understand wave behaviors, then we can understand electron behaviors. So basically what propagate means to spread or move. So pass on, that's what propagate means. So there was a lot of work and development on how the electron behaves. And we now know electrons behave like energy, and we know that electrons give off energy, and we know that they also move in a wave-like nature. So electromagnetic radiation, so what electromagnetic radiation is just energy. So it's forms of electrons, the energy that's given off. So electromagnetic radiation propagates through space as a wave moving at the speed of light. The speed of light is 3.00 times 10 to the 8 meters per second. That's how fast the speed of light is. So that's usually why we end up seeing lightning before we hear thunder, because the speed of light is much quicker. So if you look here, this is our wave, and if we start from this point here to this point here, that's equal to one wavelength. So C is equal to nu, that's what this is. That's a V with wings times lambda, which is an upside down backwards Y. So frequency is nu, and wavelength is in meters, and it's lambda. That's the symbol for them. So when we measure frequency, we always measure frequency in hertz, or 1 over a second. It's important to know that because we're going to do math problems with this. And when we measure wavelength is always in meters. The speed of light is 10 to the 8 meters per second, so it's super fast. So what it's really saying is or what we should be asking is, what's the so if speed of light is held constant, what's the relationship between wavelength and frequency? Well, if you notice here, I have a long wavelength. So if I have a long wavelength, then my frequency is going to be low. and we'll get more into that. But it just tells you that frequency and wavelength are opposite or inverse of each other. So as one increases, the other decreases. So as the wavelength decreases, and I'm just going to put a down arrow, then the frequency will increase, which means you'll have a wave that looks like, if I draw it here, you're going to have a wave that looks like this. So it's very short wavelengths. So the wavelength is how long the wave is. The frequency is how often the wave occurs. So we're going to do some problems with this, because if we understand the relationship between speed and wavelength and frequency, then we actually can basically understand, we'll understand how the wave behaves. So in conjunction with that, I'm going to talk about one more thing, and then I'm going to show you how to just we're going to work on some problems on how to calculate frequency and wavelength or energy. So if you think about this, if your frequency, so if you have a wave and they're all moving at the same speed, but if it has a high frequency, I'm not a great artist, but basically what it is showing you here is that it has a very short wavelength from here to here. That's the wavelength. So if you have a short wavelength, high frequency, it means then you're going to have high energy. So think of a slinky. When you start moving a slinky up and down in a wave-like fashion, then you're going to notice that the energy is going to take more energy to get it to be going with a shorter wavelength. So they did more research, and what they came up with is that energy of the electromagnetic radiation is directly proportional to the frequency. So E is equal to H times nu. This is the V with wings of the radiation. So E is energy in units of joules, and that means a kilogram times a meter squared second squared. And Planck's constant is 6.626 times 10 to the negative 34 joules times a second. Planck's constant never changes. Frequency, again, is in units of hertz. So as the frequency increases, the energy increases. And vice versa. As the frequency decreases, then the energy is going to decrease. And we're going to see that in some problems. When you calculate energy, energy is always in joules. So just capital J is the symbol. Planck's constant is a joule times a second. That's the units. And then frequency is in hertz, or 1 over a second. What I'm going to do is stop here for a minute, and I'm going to transition and show you how to do some of your homework problems.